Welcome to this meeting dedicated to the Spark Challenge 2021. We are very happy to welcome you here. So, I'm Vincent Godillier. I'm a research associate at the University of Luxembourg, working within the Interdisciplinary Center for Security, Reliability and Trust. And I am specialized in computer vision for space applications. Let me introduce my colleague, Mohammed.
Hello everyone, I'm Mohammed Adel. I'm a PhD student currently in Interdisciplinary Center of Security, Reliability and Trust, CVI2 team for specialized in computer vision for space application, especially for the problem of spacecraft pose estimation. Very happy to introduce you to the problem and the challenge. So first we will start explaining what is the problem we are dealing with here. Our civilization in the past century relied in our progress mainly on the space exploration and utilizing the space resources and the space infrastructure, satellite communication, the video conferences, the phones, the internet. They all rely on assets in space. But with the increased number of space objects, especially in low Earth orbit, and most of these objects actually out of service, either debris or old satellite or a small CubeSat, parts from exploded satellite or rockets, this problem became really hard in how we can deal with all this junk or space debris in flying around, with possibly to smash with important asset or important satellite and cause huge problem and out of surface for a lot of stuff. So for that, the field of space situational awareness started to emerge, and basically space situational awareness is focusing in three topics. In orbit servicing, it must be taken to expand the lifetime of a spacecraft, thus preserving the mission and delaying the creation of space debris, increasing the battery, changing solar panels, communication board, basically giving longer life to existing spacecraft. Mitigation prevention basically try to minimize the possibility of collision and the amount of debris affected by future launch. For example, if we have a part of rocket, how fastly and safely bring the rocket back without waiting for months or sometimes years and increase the possibility of collision. The last one is active debris removal, is trying to, in case there is already debris, how you can catch the debris in space and bring them down to Earth or to be burned in the Earth's atmosphere safely. To develop this technology for space situational awareness, basically we have four main stacks: identification of spacecraft or debris, localization of this space object, pose estimation, so the XYZ coordinate, the rotation, and finally the rendezvous with this space object, either debris or a spacecraft. For space situational awareness, this target spacecraft split it to different types. One type is cooperative target. That means that this target, actually we know this target and this target share information with us in shape like the location of the target or the location of spacecraft in radio signal, the XY location. So we can actually process this information and know exactly where is the spacecraft. And the second type, which is cooperative, passively cooperative, is having some kind of visual markers that we can know that this is a spacecraft you are interested in and we can approach it easily. Second part is non-cooperative target. This is that spacecraft will not share information with you or with your assets in space and this is split to two types. Uncooperative known, this means something like a spacecraft, that we know the type of spacecraft or the type of satellite, but the satellite does not communicate back any information to us besides the visual feature. And uncooperative unknown, this can be part of a debris, part of metallical part, anything that we don't actually know what is this object, just something flying in space. And on our challenge, actually, we focus in the second type, which uncooperative known in the shape that we know this is a spacecraft, a specific satellite with a specific name, and also uncooperative unknown in debris. For sensing, the sensing modularity in space situational awareness is split to two sides. The passive sensor, like infrared, the molecular camera, visible, either monocular and stereo vision, and also active sensor, like laser rangefinder, lidar, or radar. But for currently, there is a lot of research, and the current approach is adding more depending on monocular camera, because molecular camera are preferred over active sensor for the small mass, and the power requirement is really small comparing to lidar, for example, and the operation range can reach to further, like kilometers further than lidar. In lidar, for example, you can get 1, 2, 3 kilometer, but in vision and molecular vision, you can hit like 80 kilometer, and you can still zoom in and zoom out. For that, this gives us the research field the motivation that develop algorithm for image processing and target recognition and pattern recognition with space imaging is really important side. But the problem is spaceborne images have different distributions than terrestrial images. This meaning that the image we see, some like in Earth, the image we take in Earth have a different statistical signal, different noise illumination condition, different single to noise ratio, and space images have high contrast comparing to Earth images or images taken in Earth. Also, another point is spaceborne images are very scarce and costly to obtain. For Earth, we can, for example, if we are developing self-driving car, we can just go around and drive and capture videos and images, but we actually cannot do this, or we cannot do it that easily in space. Obtaining images is very costly operation. And also there is a need of benchmark of systematically evaluate compare performance of their different computer vision algorithms. For that, we develop our own SPARC dataset from our spacecraft recognition, meaning spacecraft recognition leveraging knowledge of a space environment. This obtained by on-orbit simulation environment built on top of Unity 3D with Earth model, target spacecraft, chaser spacecraft, and the camera model. And also the whole dataset is spanned with different access to add more variety in the dataset with different scene illumination, background, distance between the camera and the target, and optical sensor noise. The SPARC dataset consists of 150,000 high-resolution photorealistic RGB images, the same amount with depth images, segmentation mask, bounding box annotation for 10 different satellites, 12,500 images for each satellite, and 5 debris objects with 5,000 images for each one. For our sharing, we share with you the RGB and the depth images with the annotation bounding box. We can see in the right the distribution of one spacecraft satellite Essential 6 from our spacecraft, and we can see that we try to have like different variety from darker images to more brighter images to cover different illumination condition and also different range from very close to the camera to far away. Now my colleague will present the more specification for a SPARC challenge.
Thank you, Mohamed. So let me introduce the SPARC challenge at IEEE ICIP 21. So IEEE IC conference is the largest and most comprehensive image processing conference. It's a technical conference made for researchers, and it will take place this year remotely at mid-September, where we will announce the winners of this challenge. So as part of the IC conference, we have designed 2 image-related tasks. When I say image-related, it means 2D tasks based on 2D information. So one image classification task and one spacecraft detection task. So let's speak about the data that is available for the challenge. So the whole SPARC dataset is not yet available publicly, but a part of it is used in this challenge. More precisely, the dataset is split into 3 sub-datasets. So the training one, the validation one, and the testing one. The 2 first datasets were released, and the last one is going to be released on next Monday. So both training and validation datasets are made of RGB images with their corresponding depth images, as well as classes, so just a class label, and bounding boxes around the spacecraft in images. For the test dataset, we are going to release only the RGB and depth images and keep secret the class labels and bounding boxes. So you will have to predict them. So how to submit your results? We have already released a file that will come with along with the testing dataset. It's called the test labels participant.csv file. So you can find it already in the shared folder we have sent you the link to. So this CSV file is composed of an ID for each image, the name of the visible image, RGB image, and the name of the corresponding depth image, and 2 empty columns, the class and the bounding box column, that we kindly ask you to fill. So to be more precise, for the task 1, so the classification task, we will ask you to fill the class column with the index of each class, okay? Be careful, please fill this column with the index and not with the name of the class. And we provide here, and also in the GitLab README, we provide the correspondence between each class name and each index. So please fill it with your predictions. Now, for those of you who are interested also in the spacecraft detection task, we will ask you to fill both the class column and the bounding box column. So the format for the bounding box will be like this, between square brackets. So the coordinates of the top left corner of the bounding box in the image, then the coordinates of the bottom right corner of the bounding box in the image. So as usual, we define the origin of the axis as the top left corner of the image, and the x-axis going from left to right, and the y-axis going from top to bottom. Each participant is allowed to submit up to 5 different results. So please name your filled CSV files like this. So test underscore labels underscore your first name minus your last name minus sub followed by the digit corresponding to your submission. So 1 for the first one, and 2, 3, 4, or 5 if you want to submit several of them. Then we kindly ask you to send these CSV files by email to the dedicated email address, so sparc2021@uni.lu. be careful, the deadline is on next Thursday, so 10th of June at 23:55 Central European Time. Now I am going to present you the metrics that will be used for the change, and I will try to motivate them. So let's start with task 1, that is to say the classification tasks. So in the challenge we have 11 classes, so one for each satellite, so in total 10 satellite classes, plus one debris class that gather all the 5 images made of the different debris 3D models. So there is no straightforward approach for classification evaluation. In fact, a good classifier really refer to the actual real-world problems that you need to solve. So, for instance, if we go back to binary classification, we can define a score called the precision. That is the proportion of predicted positive that is truly positive. That means that if you put the emphasis on this metric, it means that you don't want any false alarms. Then a complementary metric will be the recall. So the recall measures the proportion of actual positive samples that are correctly classified. Here, if you decide to put the emphasis on this metric, it means that you don't want any omissions among your predictions. A common way to merge these two scalar scores into just one score is called the F-beta score. So it's computed using the formula presented here. So it's a combination of the precision and recall scores. And there is a parameter called beta that will that can be changed to put the emphasis more on the precision or more on the recall. For instance, if you choose beta equal to 2, it means that for you the recall is twice as important as the precision. If you put beta equal to 1, so the classical F1 score, you obtain the harmonic mean between the precision and the recall, and it means that you give the same importance for both precision and recall. And if you use a beta lower than 1, it means that the precision will be more important than the recall for you. So, for instance, now if we go back to multi-class classification evaluation, you can use, for instance, the same criteria for all classes, depending on your problem. In this case, you can have choose as metric an arithmetic average of the recalls or of the precisions or of F-beta scores. If your dataset is unbalanced, or you want to put more importance on one particular class, you can compute a weighted average of these scores. And now, if you don't have any specific, let's say, criteria in your problem, you can compute just the overall accuracy of your predictions. It means basically the proportion of samples that are correctly classified. In this challenge, the real-world problem that is behind it can be summarized as follows. So, if one error will be to classify a satellite as a wrong satellite. Of course, this is not something desirable, but it's not a very important problem. We call that an inaccuracy. Now, if you classify a satellite as a debris, it will be like a false alarm. For us, it means that you raise an useless alarm on something that is working correctly. So it's not really desirable. And the worst case is to classify a debris as a satellite. In this case, it means that this is an omission. So your algorithm is not able to detect the debris and classify it as a satellite. So you don't raise any alarm So it's a big issue. So to reflect that real world problem, we have derived a metric that is as follows. So first, we will consider first the debris class. And for the debris class, since the omissions are more important for us than the false alarms, we will use a F2 score for the debris class. And for the rest of the classes, so all the 10 satellite classes, we want to have balanced results, so we will compute the overall accuracy among the satellite classes. And the final performance will be given by first the F2 score among the debris class, plus the accuracy among all the other satellite classes. So this is a metric that will be used to rank your submissions. Now, for task 2, the detection tasks, we referred basically to the common COCO detection challenge metrics. So we combine both a geometric evaluation and a classification evaluation. So that's why it's very important for those who want to participate in the detection tasks to fill both class and B-box columns. So for the geometric evaluation, we will use a classical intersection over union score with a certain threshold. So if the score is above a certain threshold, we consider that the detection is correct. If it is below it, we consider the detection as incorrect. But we also want that the prediction, the class prediction, is also correct. So finally, what we will do is we will compute the percentage of predictions with a correct label and an intersection over union above a certain threshold. We will do this for different threshold between 0.5 and 0.95, and we will compute the average of these scores. Now let's jump to the report submission. So we kindly ask you to submit reports describing your method, your design choices, your test, so all the relevant information to the same email address as the results, the CSV file. But don't worry, the deadline for the report submission is 1 week after the deadline for the result submission itself. So it will be 17th of June. Now for the report, we ask you to provide like 2 to 3, 4 pages, double column format, following the IEEE ICIP format. So this will be used to help us understanding your methods and your choices. Now, the ICIP conference is accepting proceedings, in fact, for the challenges. So you also, if you want, you can also submit proceedings, so a regular paper along with your results, but here it belongs to ICIP. So further information will be communicated to you soon by the conference itself. Okay, so the reports are for us, for the challenge, and the proceedings are for the ICIP conference and will appear probably in IEEE Explore like a regular paper. Now let's talk about the rankings and awards. So we will have one ranking for each task. So one ranking for the classification task and one ranking for the detection task. Each ranking will be based on the metrics I have presented to you. And we will rank only the best model from each participant. So remember that you can submit up to 5 results. We will keep only the best one according to the dedicated metric. Then we will rank the participant based on their best models. For the task one, so the 1K euros provided by our partner LMO will be splitted as follows. So 300 euros for the task 1 and 700 euros for task 2. Also, please don't forget that if you don't sign and send back the terms and conditions, you are not allowed to appear in this ranking and to actually participate in the challenge. So please, if you did not send back this document yet, you can still do it, but please do it. So to conclude, just important information, we are going to release the test data, so both RGB and depth images, on next Monday. The result submission deadline is on next Thursday, so 10th of June, and the report submission deadline is 1 week later. Now, you know that you can contact us when you want by email at spark2021@uni.lu. You have the website, the official website of the challenge, the GitLab repository with some util code and especially the documentation that details everything that we have presented today. And for accessing the dataset and especially the CSV file, you should refer to the dedicated emails, in fact, that we have sent to you. So thank you for your attention. Now we are open to questions, and we will be happy to discuss with you and interact with you and answer if something was unclear.
Hello. Thank you for okay. Hello. Thank you for the presentation. I have a few questions. The first question, if there is any restriction or limitation to using the model, for example, if I use the object detection model for classification task, So this is the first question.
No, there is no any restriction about using any model. The restriction is basically about which task. So if you apply for this task or the other kind, you can participate in both of them. You can use the same model to do both tasks, and we consider applying for both of them. It's no restriction at all.
Okay. The second question, I can understand from your talk that there is no leaderboard to show the result of competitors. Will you send us back the result after the submission, for each submission?
Yes, after the end of the challenge and the announcement of the participant and the winner, we will share the leaderboard and the winner with everyone else.
Yes, and also to complete what Mohammed is saying, so there is no leaderboard, so it means that we won't provide you real-time feedback on your submissions, okay? You can submit up to 5 CSV files, up to 5 results from different models, but it will be like, you will be blind on which one is the best one until the announcement of the winners.
Yeah, but I mean, after each submission, can I know the evaluation metrics for this submission?
Yes, sure.
To know if I need, yeah, sure. So after each submission, I can get back.
But not the rest of.
But for me, yeah, okay, I get it. And the last question.
But also not before the deadline. I mean,
after the deadline, not.
Yeah, it's not like real time, like using a leaderboard. Okay, we don't. We will send you as soon as possible the results, but you cannot, let's say, change your models based on our feedback. You see what I mean? It's really a testing data set. It means that you can use different models based on your experiments and results on the validation data set, but not on the testing data set. Is it clear?
So I can understand that the 5 submission without getting feedback about the result from you.
Exactly. So the distributions of the data sets are all the same. So you can base your let's say opinion, and you can design your solution based on the results on the validation data set.
Yeah, okay, I got it. Okay, thank you.
Thank you.
Any other questions?
We received a few questions in our email address. I can try them maybe to see if we answered everything or not. So there was a question about the prize splitting among the tasks. So yeah, we have answered this. We have said that we will provide both visible and depth images for the in the testing data. We will have no restriction on the models, on the method you use. You can take benefit from any data we have provided. Something maybe that is not clear is the splitting between classification and detection tasks. So if you want to participate only in the classification task, you just have to fill the first column of the CSV file. If you want to participate in the detection task, you must fill both columns, okay? And if you participate, in fact, in the detection task, you are eligible to both rankings. You will be ranked for the classification task and you will be ranked for the detection task. So you can already find the CSV file in the shared folder if you want, so you can download it. Of course, without the testing data, it's a bit useless, but the testing data is coming soon, so next Monday. Yeah, so I think this is it. We had questions about like proceedings and so on. So proceedings again are related to ICEEP conference. So they are responsible to provide you information about this. Plus, we are just asking for reports.
But also, the proceeding will be good scientific contribution. Of course, if it was accepted in ICEEP, it will be included in the conference proceeding.
Yeah, so it's an added value for you. We have no information from ICEEP on the reviews of this paper, if we are responsible for the review or not. Everything will be defined by ICEEP, and they will give you this information. Any other questions?
Okay, thank you everyone for your participation, and I say we will share this video on the rest of the participants, so everyone can attend and get the information. And don't hesitate to send us email for any question related to the challenge and any information as received. And please remember to send us the term condition signed and ready.
Thank you very much.
Thank you.
Have a nice day.
So much. Thank you.